morning students. So welcome to the embedded system session. So in the previous class we discussed about what is an embedded system is. So what are the definitions for an embedded system and what are the elements of an embedded system and also how it is different from a general computing system, as well as what are the major application areas where we are going to use our embedded system. So the next topic is related to the classification of embedded systems. So this also we discussed in the previous class, where we are going to classify the embedded systems depending upon 4 different categories here. So the first one is classification based on generation. So where depending upon the generation, so we have 4 different generations and the future generation, which is the 5th generation, what we are using. So now in the first generation, so as we know that in case of our first generation, so we have only 8-bit and 4-bit microcontroller, as well as simple hardware and firmware, as well as what was the system which came into existence in the case of the first generation. Coming to the 6th generation, so we have 16-bit microprocessor and 16-bit microcontroller, as well as the complexity was still more further increased, and the systems which were implemented are data acquisition systems as well as SCADA systems. And then coming to the 3rd generation, so we have 32-bit processor as well as 16-bit microcontroller. So as well as we have application specific processors like digital signal processing and ASIC, as well as pipelining of instruction came into existence in the 3rd generation, as well as application oriented like in the area of robotics, in the area of media and industrial process control, networking, etc. So these were the major areas where your 3rd generation came into existence. And coming to the 4th generation, so it is called a system on chip generation, where we have very high performance of processors with processor as well as controller integrated together, and the smartphones whatever we are using, as well as the digital cameras, so all are related to your 4th generation. And coming with respect to the next generation, which is your 5G technology, so where we know that what is the speed at which 5G is operating and what are the numerous application areas with respect to 5G with the highest processing speed of your processor. Next, depending upon the complexity and performance, we have small scale, medium scale as well as large scale embedded systems. So we are coming to the small scale, so it's simple, and for example it can be used with respect to your the toys what the children's play, like cars, dolls, etc. Then we have medium scale, so where it has slightly complex hardware and software, and of course so it consists of an embedded operating system. And coming to the large scale embedded system, so the complexity with respect to the hardware and software is larger when compared to the rest of the 2 types of embedded systems. Then the application areas, so where it can be implemented with respect to cryptography, then process that is digital signal processing. So these were some of the highlights with respect to this large scale embedded system. And also the main important thing is with respect to high performance real time operating system for performing task scheduling. So these are all the things what we have already discussed in the previous class. Then classification based on deterministic behavior. So as I told, deterministic is it is bound to some time limitations here, so it has to meet some deadline. So based on that, so we have 2 classifications, one is hard real time and soft real time. So in the case of your embedded systems, they are hard real time, and the general computing systems are soft real time, because the hard real time has to be deterministic and soft real time they may or may not be deterministic. Then based on triggering criteria, so where like what we discussed, so we have event triggered or time triggered, where event triggered is also called as time triggered. So that means to say triggering is, it is going to perform its action only some event has occurred or when some deadline has passed, so it is going to perform its action. So that is what event triggered or time triggered refers to here, where all reactive systems like control systems in the case of controlling applications in industries use this real time or event triggered or time triggered systems. Then applications which we have already discussed, we have numerous applications from aerospace to your aeronautical to your instrumentation, etc. We discussed about elements of embedded system. So where in case of your elements of embedded system, as you can see, we have a system core. So where system core is nothing but the chip what we use for processing of our data. So where this system core, it can be a controller, processor, or it can be both, that is a combination of controller plus processor. Then we have the input which has to be given to your system core for processing of the data, and whatever the input it accepts and process, it has to produce as output. So where at the input side we usually use the sensors, and at the output end we usually use your actuators, for example your LED buzzers. And this input device sensor, so this is the sensor what we have used at the input end. And to your system core, so we have other units like memory. So where memory can be your ROM or RAM depending upon your application end, and you can also connect other supporting subsystems together with, if you want to have any communication interfaces, that also can be interfaced to your embedded system. So where this system core, it can be any one of this like FPGA, then ASIC, DSP, microprocessor or microcontroller. So these are the elements which are present with respect to your embedded system. So like microprocessor, microcontroller, FPGA, etc. So now coming to the next topic which is related to RISC and CISC. So as I told in the previous class, RISC means reduced instruction set computing and complex instruction set computing processors or as well as the controller. So what about with respect to your RISC? So in the case of RISC, as the name indicates, it is reduced instruction. That means the number of instruction which is used to process your data is less. That is, it ranges from only 30 to 40. So for example, your Atmel AVR microcontroller, so it consists of only 32 instructions. So similarly, we have what we call as CISC, it is complex instruction set computing. So where as it also indicates that complex means it consists of more number of instructions. So like it has 255 instructions in the case of your 8051 microcontroller. When you compare your RISC with respect to your CISC, as you can see here, the number of instructions is 30 to 40, and in the case of CISC we have 255 instructions. Then these are some of the differences what we have with respect to your CISC as well as CISC. So in the case of CISC, so we have greater number of instructions, and in the case of RISC we have lesser number of instructions, and in the case of CISC we give much importance to the hardware, but in the case of RISC we give more importance to the software. Then in the case of CISC, the complexity lies with respect to the processor, and in the case of your RISC, the complexity lies with respect to your compiling, because we are giving much importance to your software. So to compile your software is the complexity which is involved in case of your RISC. In the case of your processor, we are dealing with the core. So that core, in the sense, it is the hardware, that is, it can be a microprocessor, FPGA or a DSP. So anything like that. So the complexity is present with respect to the processor in case of CISC, and in the case of RISC the complexity lies with respect to the compilation of your program. That means if there are any errors, removal of the bug is the complex thing which is involved in the case of your RISC processor. Then in the case of CISC we have multiple clock cycle. So clock cycle in the sense, what is the time it takes to complete one instruction fetching, decoding and execution. So that is called as the clock cycle here, or we call it as the T state, or we call them as one machine cycle. So that means to say that, so in order to process one single instruction, so for example, if we use the instruction mul a comma b, so that means for processing or for conversion of your mul instruction to its assembly and to be executed, so it takes a number of machine cycle. So that is what in the case of your CISC, and in the case of your RISC, it is going to perform its operation in a single machine cycle. So in the case of your CISC, it takes multiple clock cycle. That means it might take 2 to 3 machine cycles in the case of CISC. In the case of RISC, it might take only one machine cycle to perform its operation. Then transistors are used to store complex instructions. That means in order to store your data, so we are going to use transistors. Then in the case of RISC, so we are going to use transistors for storing of your data. So that means for storing your memory, like to store your program. So here transistors are used to store your complex instructions. Then 100 to 300 minimum instructions, that means the instructions are more in the case of CISC, and in the case of RISC we have 30 to 40 instructions. Then in order to move the data in and out, like to the memory as well as to registers, and from registers to memory, so we require what we call as addressing modes. So addressing modes are the one which helps in accessing the data from memory or from registers, or from register to memory, or from memory to register, or from register to register. So where we are going to use around 8 to 10 different addressing modes for movement of your data. CISC, and in case of RISC it can be lesser than this. Then we have variable size or length of the instruction. That means the size of your instruction may vary. That means it can take 3 machine cycles or 4 machine cycles. That means as well as it can be 1 byte data, 2 byte data or a 3 byte data. But in the case of RISC, so it has fixed size or length of instruction. That means the size of your data, that is it is 1 byte or 2 byte or 3 byte. So it is fixed, it does not vary. So that is the meaning. So these are some of the differences what we have with respect to your RISC as well as the CISC processors. Then next we have what we call as microprocessor as well as a microcontroller. So what do you mean by a microprocessor? So a microprocessor is nothing but it is a general computing device, I can say, so which consists of a hardware, a software, as well as it has a general purpose operating system. That means you can have alterations can be done with respect to your processor, because in case of a processor you will be having only a processing unit, an input device, an output device, a memory, as well as other peripheral devices. Whatever we want to connect, so it is not inbuilt, or I can say that it is not a system on chip, but you have to externally interface all these devices. So that's why your microprocessor has more complexity involved than your microcontroller. So in the case of microcontroller, so we have a system, it is also called as a system on chip. So where it has inbuilt communication interface, then it has interrupt, timer, then we have IO ports, then so whatever we want to have, that is we have A to D and D to A converters, all these are inbuilt with respect to a microcontroller. So that means the complexity involved with respect to designing. So it's very much simpler in the case of microcontroller rather than your microprocessor. Okay. So in the case of microprocessor, so you need to interface all the devices externally. So you will be having just a processor, so where you have to interface all the devices externally to your microprocessor. But in the case of microprocessor, all are inbuilt. So that's why the complexity involved with respect to your microprocessor is less when compared with respect to your microcontroller. So as you can see, so we have some differences which are highlighted here. So where in the case of microprocessor we have from 4-bit, 8-bit, 16-bit, 32, 64-bit. Then in the case of microcontroller also it starts from 4-bit to 64-bit. So that depends upon what type of application you want and how many number of I/O ports you need. So depending upon that you can go for the bit selection of a processor or a microcontroller. So in the case of microprocessor, it's generally used in your computer systems. That is in the case of your desktop as well as in the case of your laptops, we go for microprocessor. Then in the case of microcontroller, we usually use it in embedded systems because we are using for a specific application. That means it is application specific. But in the case of your microprocessor, it is a general purpose. That means you can use for a number of applications. So because your processor is the one where you are going to reprogram it, and the hardware is being externally interfaced to it, and you can reuse once again your processor for a number of applications. But in the case of microcontroller, you cannot reprogram your controller because once it is programmed, it can be used only for a specific application like for your washing machine or digital camera, etc. It has only a CPU embedded onto it. That's what I told now. It consists of only a processing part, rest all of the devices has to be interfaced externally. In the case of your microcontroller, along with your microcontroller, it also has the memory like ROM, RAM and other peripherals like timer, counter, communication interface, etc. Then we have to connect all the components externally. So that's why the complexity involved is larger in the case of processor, but in the case of your controller, all the components are internally connected. That means it is already inbuilt. That's why the size, the circuit complexity is less and the designing is also simpler in the case of controller. Then in the case of microprocessor, it consumes more power because you are interfacing each and every device to it. So that's why the power consumption is more. And in the case of controller, it consumes less power because already all the devices are inbuilt. So if you just pass the power only to your controller, so it is going to pass the power or distribute the power to all of the devices which are internally connected with it. Then it has very less internal storage. So that means the storage requirement in the case of processor is less. That means we need to have an external memory interfacing is required in the case of microprocessor. In the case of your microcontroller, so since we have many registers, so we can store the data inside your registers rather than going for external memory. So these are some of the points related to your processor as well as your controller. So and the next topic is related to sensors and interfacing. That means we are going to study what is a sensor is and what is an actuator is and how we are going to interface these to our application areas like for your home automation as well as for your industry, for automation, etc. So before that, let us see what do you mean by sensors as well as actuators. As we were discussing with respect to elements of an embedded system, we saw that sensors are the one which are present at the input end and actuators are the one which are present at the output end. So what is a sensor? So you know that all your embedded system, so they interact with the real world and they are going to control or monitor the functions executed by the embedded system. So how they are going to control or monitor the functions? So that is in accordance with the changes whatever is happening with respect to the outside world. That means anything is happening outside, so that is being monitored. For example, weather forecasting. It might be a sunny day and it might be a rainy in another day. So how these changes are being monitored? So these changes can be monitored with the help of what we call as sensors. So which are going to control or monitor whatever is being happening outside the real world. That means, so it is going to sense and it is giving as an input to your processor for further processing. So the changes in the system environment or variables are detected by sensors which are connected to the input port of the embedded system. As I just told, so whatever the changes happens within the surrounding environment, so they are being captured with the help of your sensors, and with the help of sensors which act as the input, it is being connected to the input port of your embedded system. Now if depending upon what application we have designed our embedded system, so depending upon that, so we are going to, the sensors are going to perform their operations and they are going to produce the desired output. So here how we are going to, whatever we have sensed, so it is with respect to your sensors. Now what changes it has been sensed, so that has to be known now. So how it is being done? So it is being done with the help of what we call as actuators, so which are being connected at the output end of your embedded systems. So like sensor is nothing but, so it's a transducer that converts energy from one form to any other form for any measurements or control purpose. For example, temperature sensor. So what is the purpose of temperature sensor? It has to monitor the surrounding temperature, where the temperature it will be in terms of centigrades or Fahrenheit. So now only the electrical signals can be known by our device. So that's why whatever the temperature it is sensed, so that has to be converted to electrical signals, that is to analog signals, and then only it will be further processed. Then similar to temperature sensor, we have other type of sensors like humidity sensor. That means it is going to tell what is the humidity level. Similar to that, we also have fire sensors, moisturizer sensor, ultrasonic sensors. It is depending upon what type of application we want, or what we want to monitor, or what we want to control. So depending upon that, so we are going to use that type of sensors. Then we have actuators. So where it is also another type of transducer. So where an actuator, it can be a mechanical actuator or it can be an electrical. That means it can be a mechanical transducer or electrical transducer, in the sense it is going to convert from mechanical energy to electrical energy, or from electrical to mechanical, vice versa. Okay. So where here your actuator is the one which is going to produce its output depending upon some motion. Like for example, if you have connected a stepper motor across your output, so it is going to rotate depending upon whether you want to rotate your stepper motor in the clockwise or anti-clockwise, or for what application you have used your stepper motor, whether you have used your stepper motor for rotating action. So anything to happen, so that is done, or that is indicated with the help of your stepper motor, where actuators are the one which is connected across your output, and it is going to tell what physical action it is going to perform depending upon what input it has been sensed. So what do you mean by instrumentation? Instrumentation is nothing but it is the technology where we use some measuring instrument to measure some quantity. For example, what is the amount of milk, what is the weight of a person, or it could be with respect to any weighing machines. So we use the instrumentation. So where, as you can see here, so we have a block diagram of an instrumentation system. So where in the block diagram, as you can see, so the input will be a physical quantity. So what is this physical quantity is? So physical quantity means what you want to measure. For example, it could be anything. Here what we have considered is a temperature. So where you are going to sense the temperature, so which is the physical quantity, where the temperature is being sensed with your sensor. So Sensor is going to sense the physical quantity what you give as the input, where it could be temperature, pressure, velocity, etc. So after it is being sensed with the help of a sensor, so then we have the next block, which is nothing but a signal conditioning system. So what is the signal conditioning system? If you have any error with the captured data, so we are going to condition our signal. That means we are going to remove the noise which is present with respect to your signal which is being captured with respect to your sensor. So once the signal is free with respect to the noise, so then we are giving it to a signal processing unit where it is going to further process the signal. That means, so the input quantity what we have captured is temperature. So that temperature, if you want to measure in what unit we want to measure, so depending upon that the signal will be processed. For example, your temperature is being measured in terms of degrees Celsius or Fahrenheit. So the processing part will perform the operation of converting your temperature to Celsius or to Fahrenheit, or if you want to measure your voltage in terms of volts or current. So that can be done with the help of your signal processing unit, where along with your signal processing unit you can see we have two more units which are connected. So one is the display section. So where the display section is the one which is going to have a display unit. So where it is going to display whatever it is being sensed with respect to your sensor, that will be displayed on the display board. And similarly, so the recording unit is going to tell you what is the temperature which is being recorded. So where you can store that for further purpose. So then your data output, that means your temperature what it is being sensed. So after it is being processed, so you can connect that to some other device. So this is what an example for an instrumentation system. So the main blocks which constitutes your instrumentation system. So as I said, the physical quantity, then we have the sensor, then we have the signal conditioning system. So where this noise will be removed and then the signal will be processed. So that means you can process your signal with respect to either in terms of digital. If you want to display, you can display your data in terms of digital, or if you want to display your data in terms of analog, so that can also be done here. So where if you want to convert your data from analog to digital or to digital to analog, so you might require a converter like an A to D converter, or it could be a D to A converter. So that is about the simple block diagram what we use in order to measure any quantity with respect to any instrument for that matter. Okay. So now we have control system. So what do you mean by control system? So control system is nothing but where you are controlling the input by having some feedback. So where the feedback can be a positive feedback or it can be your negative feedback. So as you can see in this block diagram, so we have used or we have represented a control system. So where we have used a negative feedback here. So where whatever you have sensed from the output, it is given as a feedback or given as an input, where you can see at the input end we have an op-amp. So where we have inverting and non-inverting terminal. So to your non-inverting terminal, we are sensing the input or we are giving the input. So suppose if your input has any deviation, so then that corrections are being done with the help of this feedback signal, that is a negative feedback which is connected from the signal conditioning system with the help of the sensor output. Then we have this positive and negative terminal to which the input as well as the negative feedback is connected. So this is a comparator circuit. So where the comparator work is to compare the two inputs, and depending upon the comparison, it is going to predict what is the error, and after you have any error with respect to your input signal, so then that is being removed with the help of your power amplifier, and also it is going to amplify your signal further processing or removing the error and amplifying will be done with the help of your power amplifier. Then from the power amplifier, so the output is given to a control device, where the control device can be any one of this. So as you can see, as I told, so we have a negative feedback, so it is used for removing the error, and the input, that means here the error signal, so it should be 0. That means after you perform the comparison of your input with the negative feedback signal, whatever the error you get or the output you get from the comparator, it should be equal to 0. So once the error is nullified, so you can further process your signal, where it is given to an power amplifier to amplify a low. If suppose if your signal has been reduced, the signal can be amplified with the help of a power amplifier, and then it is given to the next block. So where we have what we call as a DC motor or an actuator or a heater. So this is the control device, so which is being connected from the power amplifier. So for example, you suppose if the speed of the DC motor is more, so then that can be reduced with the help of the feedback signal, or if suppose if the motor speed is very less, you can then increase. And also we have one more application, that is heater. So where you can control the heater, that means depending upon the temperature of your room, so the heater can be controlled, whether if you want the temperature to be increased or decreased, that can be done with the help of your feedback signal. So this is how the block diagram or the blocks with respect to the control system is going to look like. Okay. So that is input, where you can give any input to your device. So from the input it is being amplified, and from the amplified signal, so it is given to a control device, where you are going to control whatever the device which is being connected at the output end. And so this sensor is going to capture the signal, so whether the DC motor is running fast or whether your heater is heating at a very faster rate, or if you want to make the temperature of the heater to be low or to increase, that is being sensed, and it is given to the signal conditioning system for further processing of your sense signal, and it is given as one more input or negative feedback to your amplifier for comparison of your input and deciding what has to be done, whether to increase or decrease the speed of a DC motor, or to increase the heater temperature or to decrease the temperature of the heater. So this is about the control system block diagram explanation. So next topic what we have is called as transducers. So as we know that we cannot use only one form of energy in nature. So even though we have the energy available, like we have solar energy, wind energy, light energy. So now we should have some conversion process to convert from one form to another form. So if suppose if I want my solar energy to be converted to an electrical energy, so then I need to perform some process. So how this can be achieved is with the help of what we call as transducers, where transducers are the devices which is going to convert the energy in the form of sound, light, heat into an equivalent electrical signal, because every signal so has to be converted to an electrical signal, or it could be an electromechanical, or it could be a mechanical signal. So now we have taken an example here for representing a transducer, where a loudspeaker. So loudspeaker is a transducer which is going to convert a low frequency signal to a higher frequency signal. Similarly, we have considered one more example, that is a microphone. So the purpose of the microphone is to convert your sound waves into a wave formation. So that means it is going to convert into sound pressure variations with respect to its voltage or current. So as you can see, these are the two examples what we can consider to represent a transducer. So where it is going to convert one form of energy to other form of energy. In the first, so we have converted a low frequency signal to a high frequency signal, and in the second case we have converted the sound signals into an equivalent voltage or current variations. Transducers, it can be used as inputs to electronic circuits, and also we can receive the outputs from them. So for example, your loudspeaker is an output transducer designed with respect to an audio system. So because when you speak, so your loudspeaker is the one which is going to amplify your signal. So that's why your transducer need not be an input, it can also be an output as well as an input. So microphone, so your microphone is an input transducer where you are speaking, and that signal is whatever you speak, that is a speech signal, is being recorded and it is being converted to variations of sound with respect to its voltage as well as current. So your transducer can be both, or it can act both as an input as well as an output. Then sensors we have already discussed, so where we have different numerous types of sensors. So where sensors are the one which is going to sense the signal with respect to any physical quantity such as distance, velocity, acceleration, temperature, pressure, light, etc. So then depending upon what type of application you are going to use, the sensor can be chosen. So depending upon the application, you are also going to choose the sensor looking into these criteria, like what is the accuracy of the sensor, what is the resolution, what is its cost, as well as what is the size of the sensor. Then sensors are also being classified into two types, that is analog as well as digital. That means if you want to represent the signal, the sense signal in terms of digital, so where you can also display them in terms of digital. So digital means it can be in terms of on and off, or it is an active high or an active low signal, or it can be a logic 1 or logic 0 representation. So but in case of analog representation, whatever the speech signal it is going to sense, so the output will be in terms of its voltage and current. It is nothing but it is a waveform representation, or it will be have a continuous variation of the signal with respect to its voltage as well as the current. So that is related to the sensors as well as the transducers. Then we have a topic related to LED, that is LED stands for light emitting diode. So LED is also an important output device for visual indication with respect to any embedded application. So where it is going to be used as an indicator. So for example, it is used to indicate the status of various signals. For example, whether it is on or off. If suppose if the LED glows, then it indicates that it is in the on condition, and if it is in off condition, and if the LED is in off, so it states that it is in the off condition. And also it also indicates the charging of your battery condition. And as you can see, so it's a simple, so LED will be having a simple circuitry where it is a simple PN junction diode. So where it consists of two terminals, an anode terminal as well as a cathode terminal. So where anode represents the positive terminal and cathode represents the negative terminal. So where you can see, so the anode is being connected to your VCC, that is plus 5 volts, and the cathode is being grounded here. So now since the LED cannot resist a large amount of current, so we are going to connect a resistor in series with respect to your power supply. So it is called as the current limiting resistor, where it is going to limit the amount of current flow which is entering to your LED. So the ideal LED interfacing circuit is as shown in the figure. So where you can interface your LED in two fashions. One is with respect to common anode fashion, another one is the common cathode fashion. So where in the first method the anode is being directly connected to the port pin and the port pin is going to drive the LED and the port pin sources current through the LED when the port pin is at logic high. And in the second method, so that is nothing but the common cathode configuration where all the LEDs will be connected to the pins of the cathode and the anode to the supply voltage with the help of a current limiting resistor. And also here the LED is turned on. So where in the case of first method the LED will be on when it is at logic 1, but in the second case the LED will be turned on when the port pin is at logic 0. So that is the difference we have with respect to common anode and common cathode. So anode means it is 1 and cathode means it is 0. So that is why here for the common anode configuration or common anode connection, the LED is going to glow only when it is being connected to logic high condition. So in the second case, since it is a common cathode configuration, so it is going to give its output only when it is connected to logic 0. So now we have the representation of this 7-segment LED display. So where in the case of 7-segment LED display, so we have used this device for displaying alphanumeric characters. That means you can display both alphabets as well as numbers. So that is why it is called as, that is why it is an output device which is used for displaying alphanumeric characters. So where if you, so this picture shows so how we are going to represent an 7-segment LED display. So where you can see we have a dot, so where that dot represents DP. So LED segments are named from A to G. So starting from this, so this represents A, B, C, D, E, F and G. Okay. So then one more is, that is the decimal point LED segment, it is named as DP, and depending upon the representation, so it is going to display all its numbers as well as characters. So this is once again the common cathode and common anode LED display. So as you can see here in the case of common anode display, so your anode terminals are connected, that is your anode terminals are connected to positive supply and all your rest of the pins are being connected to, so this is your positive and this is your negative terminal. And in the second case, in the common cathode, so all the port pins are being connected to cathode and the supply is being connected to the pins of your LED. So here the current with respect to each, that means as you can see, so we have to connect a resistor so to limit the current, and the current what we can limit is up to 20 milliamps. So the current can be limited with the help of a series current limiting resistor, what I already mentioned. And this is, since it is very low cost, so you can use a 7-segment LED display in case of public telephone call monitoring devices. Then with respect to your display, so you can wherever we have this display option, so you can also use this 7-segment display as an output device to display the numbers, so as well as the characters can also be displayed with the help of your 7-segment display. So these are the topics what we have with respect to your embedded systems. So where if we summarize, so we started from the definition of embedded system. So what is an embedded system and how the embedded system is different from other computing system, and what are the differences we have with respect to a general computing system as well as an embedded system. And then different classification of embedded system. So, where we have 4 different classification of embedded system, and then what are the major application areas in which we are going to use our embedded system, and different generations and different performance criterias, and then depending upon deterministic behavior and depending upon triggering. So, we have different classifications of your embedded systems, and then we saw what are the differences we have with respect to an microprocessor as well as a microcontroller. Then what are the important elements of an embedded system. After that we studied related to the differences with respect to a RISC as well as a CISC. So, what is RISC as well as what is CISC, and which is more helpful. And then we have small topics related to sensors, the definition for sensors, and what are actuators, and what do you mean by instrumentation, and what is a control system. Then what is a transducer, what are the different type of transducers we have, and the simple interfacing output device like an LED. So, how we can interface an LED to your output device, and later on we studied about a 7-segment LED display. So, where it is being used for displaying alphanumeric characters. Thank you.